Okay, so we're going to be starting now, right? Hello, everybody. My name is Alexander Korotkov from PostgreSQL, and I'm going to share my presentation, which is called the bottlenecks of PGSQL, part 2. Now, what is this about? Now, the point is that I was giving a presentation on our previous conference where we had the collection of cases, how Postgres was working, and then all of a sudden stopped. We have part 1, and it seems that the previous time the audience found it interesting. And over a year, I have managed to get more cases and more thoughts on the subject. And once again, I want to say that what I'm speaking about, I'm not saying that it's necessarily the most widespread cases. And I'm going to look at 3 cases. The first case is when we have got stuck with buffer mapping clock. The second one is when we got into proc lock, and the third case is when we are in the mechanism of fast path locking, we ran into collisions. There, I'm saying lots of strange words, but as we are going on with the presentation, I'm going to do my best to explain them. Okay, so let's go. Case number 1. Well, an almost eternal waiting for the buff mapping lock. Now, how to replicate this case? In order to replicate this case, we will require this Amazon virtual server for Intel cores, and it's like Amazon thinks it's 36 physical cores, but according to our modern day scale, people have larger scales. We have a lot of clients who work on larger clients. PostgreSQL with slight changes, the simultaneous commit, and we change the max connection somewhat. Now the case is as follows. 2 testing sites, and one of them we filled up as a reference point with a number of testing values, and the other one is initially empty. Now, what do we do with these test tables? We launch 2 parallel scripts of pgbench, and the first script takes 30 values from the reference field. Each time it is the same 30 values every time, so it turns out it's 30 lookups through an index. The second one, and thereby, because our reference book is fairly limited, we only have 1 page that fits, so you see that we have a gbench script that continues to work with the same pages over and over again. In real life, it's unlikely you will find a similar inquiry, but maybe you have some loop join thing, which it could be very similar to a reference book. The second script is just filling up of the second table with random values. And what do? We launch the first script with 150 instances, and we launch the second one as a second instance. And so we intensively take out 150 flows from the reference and streams from the reference, and then we also get 1 more. And so there's nothing surprising or nothing super specific about this. Somewhere you have set amount of loads, somewhere you have select heavy loads. Now, the first script gives us approximately 60, 65 GPS with a slight variation, and the second one, from the beginning, it was giving some weird TPSs, and then all of a sudden it just stopped and went down to 0, and we could be waiting for it like this for 10 minutes, and nothing would happen. Now, what really happened here? Who is to blame? It's an existential question. Now, we're going to try and answer that. Who is to blame? Trying to find out who is to blame, we're going to be doing the detective work on easy mode. It's going to be fairly easy. We have a viewer which is called PGS test activity, which has the wait events. And with the wait events, you can see that this process that has been carrying out the stack is stuck on the overlock, which is called the buffer mapping. I understand that this information is going to is going to say anything to anybody, to only the people who understand how Postgres works in its internal mechanics, but we are going to try and dive into this right now together. So who is this buffer mapping, and why did it get us stuck? Now, to understand this, we need to remember that there is a hash in Postgres that displays the number of the block, which is on the disk, and that it reflects to the block that is in the shared memory. So we have hash, and this hash inside the memory is responsible for understanding whether this block is cached, and if it's cached, then where is it cached? Well, the hash table, how does it work? If we are to simplify this, we have a certain value that we want to search for. We count the hash starting from it, and then according to this hash, we look up the number of the bucket, and if the hash function is good and we have few collisions, then this bucket is small, and we can quickly sequentially look through the elements and find what we need, or not find what we need. But this is how hash works in the cases where we have only one thread or one process has access to it. But what happens if we want the hash? If, for example, a number of processes were working with the hash, in this case with the Postgres and the backends and the system processes are all working with this hash, we separate this hash into its locks. The so-called locks, so we overlock. So we close the buckets with a number of one lock for many buckets, and to get access, we need to either get shared or exclusive locks. And so just to find the buffer, we take the shared lock, and to find the exclusive lock, to move the buffer somewhere, to change it, we have to take exclusive locks here. Now, this is also probably fairly hard. Now, what is an overlock? And so in order to explain what is an overlock, I decided to prepare these humanly understandable illustrations, these very current. Now imagine there is a certain booth where they are accepting documents. People would walk into it, and people are coming in to submit certain documents, but there are these sneaky people who come in to just ask for something without actually submitting anything. So let's imagine this person who is in this booth, he just gave in his documents, submitted them, and then the next one comes, everything is good, but the trick is that the people who want to just ask something, let's say they come, two of them come in at the same time, they walk through it and at the same time, and then the last one is already processed and so on. And so far so good, everything works. Some people are supplying the documents, some people are just asking. It's okay, the bureaucratic system of the government is flourishing. But where is the trick here? Imagine the two people are asking here for something, and a third person comes in, and he also wants to ask, and this person decides to bypass the queue and to ask what he needs to know without standing in line. And usually everything is fine. If there is not too many people asking these questions, then it's okay. But what can go wrong? It can be the case that the flow of people who require to ask something is never ending. They're always coming, always asking to go without a queue, and they do not stop. And this person who needs to submit the documents is standing in the queue and waiting eternally to submit his documents. And the same thing happens in Postgres. So we have these only read-only requests that are always going to this hash to constantly find the same buffer, and they have taken up this lot fully, but the process who needs to do the insert, he needs to select a new buffer in order to insert something into it, to insert new data into it. And so it comes to that point that he has the partition which is fully booked out and fully blocked. And so this process of insert is this poor person who is waiting to submit his documents, and he is never submitting them because these people just don't end. Now, what can we do? Trying to respond to this, I'm first going to show you a human interpretation, and then we're going to see how that works on our technicals. Now, what should this person do? Now, the first solution, that which is very self-evident, that we just have too many people. So we have too much load on our bureaucratic system. So we have these great assistants of the government here who are called the viruses. You've heard about the coronavirus. It is a great tool in order to reduce the population, who always walk around and are always asking something and want something, and you can just kill off the excess population, and we'll just get the good people left who are going to be serviced by our bureaucratic state, and everybody will be happy. And now we're moving towards the technical side. Now, in terms of the technical side, it just means that we have too many cores and too many processors in our server. Because of this, these processors are running many processes who are always trying to get to these shared resources and can never get access to them. In this scenario, we can recommend to either buy or to rent out a worse server who would have less cores to not get into this limit issue. And of course, this worse server is not going to manage to work with your application. So you need either to limit what you want to do, or you need to limit how much Postgres has access to your processors. Now, option 2 is to limit the access to your bureaucratic state booth, and we need to just put barbed wire all around it, and we put the armed guard next to it, and if he sees that there are too many people around, he's just going to tell people to go screw themselves and go far away and quick. It's also a working option, but the people, though, who are able to get past the barbed wire, they will be able to conduct their business in an orderly fashion fairly quickly. Now, let's imagine let's go to the technical world. That means that when we have too much read-only load, we need to somehow limit it. So either on the application level, we have to make it that we don't have so many connects, or there are load balancers like the PG balancer, Odyssey, the person who was the previous presentation just before me. And so through Odyssey, you have the full potential capability to have a lot of connections to Odyssey, but then less to the Postgres itself, and this is how we can solve the issue. But jokes aside, all these are not our methods. You understand that if the presentation is being made by a Postgres developer, I will be able to show you a solution on the basis of the actual database. Now, the first solution is a very true solution. We have to remove the conflict. So now we make a model window to accept the documents and a separate document where you can ask. And now all the people who want to submit the documents, they're standing in line in order to submit their documents. And the queue is one by one. It's consequential. And if you have stood in line, sooner or later you're going to get it. And in the ask window, they can ask 5 at a time, 6 at a time, and they're not going to get in each other's way. This is a great method, but technically it is fairly difficult to implement. Now, the idea here is to try and fix the use case of this overlog so that we would not get into a situation where we have a lot of shared people coming in and who are not letting the exclusives through. Yes, and in the Postgres community, we hear the conversations about these sort of patches that we need to just remove the hash table on the locks and to instead create a correct tree-like structure which would be lockless and no locks, and it would be just happiness for everybody. And the same would be true for all the other overlogs who are in for the same types of contentions. At least in concept, these solutions exist, but they're hard to implement and they will take a long time, and it probably will be done at some point in time. But we do need a solution right now because we have errors and nothing works right now. The next solution consists of the fact that if this person who's been waiting in line for his queue, and now he got real pissed, and he told all these noisy nuisance people to go and get in line. Now, they got in line, and this person started to calm down because he understood that there will be a point in time that he will be able to submit his documents, but he's waiting for all these current people who are asking questions will finish, and then the process will go on just as usual. And let's call this the honest quotation marks queue. Now let's move on forward. Now, what does this honest queue mean in terms of our equipment now, technical side? Now, the patch is called the fair overlog as the more honest, more fair overlog, because the whole thing where shared goes without line, it doesn't seem fair. Why do some people have to queue up and some don't? Now, the idea is in the fact that we are introducing the goods change. So we have a user setting where the overlock share is the limit, and then it's a consequence of shared overlocks, and this passes prior to when the overlock goes into a private mode. So this setting is responsible for the patience of the person who's standing in line and waiting to submit his documents. And when he goes into the honest mode, all the shared locks, all the people who are trying to go into the queue without to surpass the queue are actually going to be honestly standing in the queue. And so when the exclusive locker goes by, when this person submits his document, the honest mode is removed, and then the next exclusive locker will be once again putting the system into the honest mode or fair mode when the time comes. Well, it's clear that this approach can also have certain overheads because this unfair behavior of the overlock is there for good reason, because it is able to very positively affect the performance. Here you see the PG drive of the bench. If we will have the overlock as 1, and we have a really good penalty on performance, in certain cases it can be almost double or triple. And if we put it as 16, if we have the patience to let 16 people through ahead before us, then we see that the overhead is not as big. It is varying in around 2 to 3%. And what are the results of the patches that we see in this case? And we see that it gave us 60, 65 TPS. It's still doing the same thing right now. And maybe if we take the measurements with the proper watch, maybe we could see a statistically significant deviation, some regression, but I actually didn't do it. And the other script actually gives this out on a stable TPS, and this is what we need to do. Nobody stands dead in our situation, and this is great. But unfortunately, we're unable to patch into the upstream of progress. We're unable to commit it because the community of Postgres is very perfectionist, and they're saying let's not fix the overlock because the overlock has a certain pattern of load and the use case is wrong. So we would need to implement the previous decision, and these quick life hacks, let's not use them in Postgres. So what should the users do? Now, if you have money, just buy Postgres Pro Enterprise and don't bother with it, because in Postgres Progress, it has all of it. Our support engineers will help you do it. Now, if you don't have the money, you can go into mailer lists, apply the patch, apply to Postgres, and use the support from the mailing list. So if something collapses, you can use the mailing list to ask the question. It'll also be a good idea to be a conscious participant of the community and to share your experience in a thread, and it'll also be good to say to Andres Flund, he's also a senior community member, a committer who is the main opponent of this patch, to tell him that he is wrong. And maybe this will lead to something. No. I think that's it with this case. And the next case is the pro-Harley lock. The proc array lock can go into the same place as the buffer ping lock, but I'm going to speak about this in more detail now. But first, I'm going to talk about the work that has already been done of the proc array lock, once again, using the example of submitting the documents to a booth. Now, what is the point? The point is that there is not only the problem with the people asking without going to queue, but there's also a problem that the people who are going to submit the documents, they can only enter one at a time. And what can the possible optimization be put in place? So the person who's standing in line first says, hey, you can send me all your docs, and guy can just go in and hand in all of your docs at the same time. Everybody trusts each other, and he goes in and he submits it all by himself and he comes back. And so there is no overhead for everybody to get in and out. From the technical perspective, this would look like you have a certain overhead to switch processes. And if we have a queue, we have a number of processes queued that are all waiting for the lock, and they are one by one taking in the log. The next process wakes up, does something, then wakes the next one, goes back to sleep. This takes up a lot of time. And if this first process is going to be doing the work for everybody, it's going to be much quicker because the operations in the memory are very cheap. And to put to sleep, to wake up, these are fairly costly operations. And these optimizations have been applied. We have the proc array lock in Postgres, which protects the information regarding which processes in progress are currently working. So this lock is applied in the commit, in the background work when they're completed, and when we connect new backends. And so in Postgres 9.6, we already had this optimization appear because the commits would commit as groups. So you have a number of backends which are waiting to commit, and instead of them doing this one by one in a queue, the first one is just filling them up in batches into the shared memory, and it turns out that this is more efficient. And onto the commit, we see the C-lock apply. We see the information about the C-lock, whether the transaction committed, aborted, or applied. And once again, the C-lock, everybody's trying to apply the C-lock to push through their status if you have a large amount of transactions. Now, once again, the first one who's standing in line can just do the work for everybody else, and it turns out that it's faster. Now, this helps a lot when you have a strong load. The performance improves, but in a number of cases, this does not help. Now, let's look at how can we replicate the situation? How would we run into it? Now, we have the same setup, we have the same virtual server, the same server conf, and now we run a simple script, select 1, select 2, and we go on until 30. 1, 2, 3, 4, 30. And meaning that for one query, we're counting 30 different expressions, and we are launching the same in 150 of those. This is in the sort of benchmark to Postgres. Now, what happens is that this benchmark gives us 35,000 TPS, which is not bad. But the problem is that after it, you are unable to just enter the database with the PSQL. And the worst thing is, if you look at it through PS, you see that 150 backends work and 33 are stuck on authentication stage. So even the PG bench is unable to load through their connections because this log has been so shut full that the PG bench can't even connect his own processes, and there is no way that you can connect to the Postgres as well. Now the situation is very not nice. Let's just put it this way. Now, who's to blame? Now, the thing is that in Postgres, even if you are trying to calculate some constant query, in this case it's select 1, you still have to take a snapshot. And so you take a shared lock on the snapshot, and in this entire construct, when you're calculating something, it just fills everything up with the shared locks, and it's fully now that lock is fully locked, and you can no longer do anything about it. You can't connect, you can't put a new transaction through. And what can we do with this? Now, the first thing that we can do with this is decrease the load, and we have gone through this in our previous case. Then we have a patch for a more fair overlock, the same one we used in the previous case. It also helps. But there are two more recipes we can use. First one is the so-called CSN patch, and the other method is that we can optimize the load. And I'm going to speak about this in detail. Now, what is the CSN patch? To understand what is the CSN patch, we need to understand how do snapshots work in Postgres. What is a snapshot? Each transaction has a number, and a snapshot is a structure of data according to which we can understand what transactions for us are in the past and what are in the future. Which ones are in the future. Now, the thing here is that transactions are numbered with accordance to the time they started, and we need to understand the future and the past according to their commitments. To their commit. So we have the snapshots which go from xmin to xmax, and the transactions, the SIP that goes, those SIP, the ones that are in progress go through SIP, and we understand that everything less than xmin has been committed. Everything that is either larger or bigger than xmax has not been committed. And the ones that are in progress have also not been committed. So these transactions that are listed here. Now, thanks to this, with this structure of data, we can understand what has already happened and what is going to only happen in the future. Now, what is the drawback of this model? This model has been invented back when Postgres, well, let's say, just worked on the machine of some 1990s, some old server, which was just a motherboard and two single-core processors. Back then, that was a great server, and I don't know, we would have 10 or 20 backends working, and the snapshot was very compact. You had only a number of numbers. But imagine now, when you have 1,000 connects, now this snapshot just becomes bloated, it becomes huge. You have an enormous amount of parallel transaction, and this snapshot becomes a fairly cumbersome structure. Well, relatively, of course, which we need to gather together, and we need to gather it together under a lock. So it's going to take a fairly long time. We'll have to lock it for a while, and everything just becomes lock. And so in modern conditions, this model is starting to outlive itself. Now, what is the idea of the CSN? The CSN is the idea of CSN is that we don't only number them by their start time, by their XID, but also we give them a certain number in the order of their commitment. And then the snapshot turns into a single number, into a CSN. And in this sense, everything is great. But then we come across a different problem. We need to somehow, these XIDs that we have and that we store in the database, where we treat them with visibility, we have to somehow use them in the CSN. But practice shows that this problem is somewhat easier to solve than to solve the previous problem with the snapshots. Now, we have a patch for CSN. It is there in the mailing lists, and we have a benchmark where the load is 90% on the 90% comprised of reading and 10% of writing, and we could get plus 50% to performance with the use of CSN, and I think that this is very good. But this is not the only thing that we can do. To be in reality, we can be somewhat tricky about it, and we can modify our script that runs the benchmark. We can add a select to it, a select of the function that is called a TC-card. Now, what does this function do? Now, this function returns us the previous number of the transaction. Now, what is the point? The point here is that the transactions that are read-only are not assigned to exceed. They're only assigned to the read and write transactions. And when we summon this function into the read-only transactions, it automatically makes it a read-write transaction, even though we did not read or write anything. And as a result, this transaction is also going to be taking the exclusive locks to proc array and is also going to write something into it. And in normal situations, this only makes everything worse because we are forced to take a stronger lock. But in our case, when we have fully filled up this lock, and when we try to only use it in the exclusive mode, we are trying to fight fire with fire, and really we are able to get 34,000 GPS with this modified script. In comparison, it's a 3% decrease in performance, but we have everybody connected, and all the processes on the Gbench have also connected to the database, and you can also connect with the PSQL, and everything just starts to work. Now, this is a hack that you can apply without any patching of the original source code of Postgres. And one more case. In Postgres, you have a mechanism called fast path locking, which works great, and thanks to which we do not experience significant overheads on the blocking of relations and so on, but which sometimes can break down. Now, if we are to illustrate this with the same booth for submitting your documents, then fast path locking is not an exact analogy, but we can try and present it as the following. We have a place submitting documents. We have a little window here, and we have a separate place with information. And some people go to submit documents, and some people just read the information, and they're fine. But we can replicate the database for the Geekbench, and we can take some interesting functions in GitHub that I wrote down but that are too long to be written on a slide, but these functions will create a collision. So we're creating a normal table that will not have any collisions, and we're calling forth this function with the probability of 1024. We can have a fast path collision locking in our table, and 1 out of 1024 is not a event that is too rare to not happen in real life. And now let us compare what happens in the cases where we do have a collision and the cases where we do not have the collision. And the point of the script is that it takes a strong lock on the table, and in this case I wanted to do a truncate of the table. This is an operation that requires a strong lock and requires access of the exclusive lock.
So actually this is not intervening with the script which is in operation. The script performs the select of the table, and this script will truncate some separate table. And in parallel, we start PGB read-only with 150 threads, and with 10 threads we perform truncate without collisions and with collisions. And then we look at the results. If we are doing it without collision, then select only will be 840,000 TPS. This is a quite good result. And without collision, we truncate of the table of 250 times per second. And with collision, the performance of read-only TPS will decrease by several times. But the performance of the truncate will increase slightly, but I do not think that this is a good result overall. So what's happening? Going back to our analogy with our booth, I draw it in a way that this queue of people who are going to submit their documents is not in the right order, and they blocked the information point, and this guy who just wants to read something, he has to stay in the queue, although he just needs to read some information. So what do? First, we should not take strong locks too often. Ideally, we should use Postgres in a way that strong locks will not be necessary too often, maybe just for some maintenance. I understand that there are lots of people who like temporary tables who will disagree with me, but this is my opinion nonetheless. Some queries which... Okay, how you monitor this? If there is a query where you know for sure that there is no strong lock, for example, just a select who just reads, or some update or insert or delete which touches upon only the rows, and you see that they are hanging in wait tab lock manager, this is suspicious, and if this happened, then something is wrong. And the recipe is simple, just to change void and it will disappear. You just recreate it and it will get a new void. So with big probability everything will be just fine, and if not, then you can repeat this operation. So this has been the conclusion, and these were the cases which I wanted to share with you. I hope you liked at least the funny pictures. Thank you. I've put a lot of efforts into those pictures. Your questions, please. Thank you very much. Please explain the level of isolation in the second case. Repeatable read is not the solution. Repeatable read, yes. Yes, it will improve the situation, probably. I did not check myself, but with repeatable read, snapshot should not be done for each calculation, but it needs to be checked. Last time I checked the code, I was surprised negatively, but later I will check and I will be able to tell for sure. Spin lock and lock logs are existing in Postgres. Spin lock is available. Latch, this is a physical blocking. Let's say the first problem. This log will be logical. This log is a low-level primitive, and it's one variable within the memory, and the operations, atomic operations, will be processed. And hash collisions is the standard system of collisions. They will be solved in other databases by means of increase of the number of files. So you distribute the table within more files, and the latch probability decreases. Yes, in principle it's correct. In fast path locking, I didn't review technically this mechanism too much in detail, but it has 1024 atomic variables in its memory, which store how many strong locks is contained in this hash partition. And if it's 0, then the weak lock can be taken, and you can simply increase this number, make it not 1024, but much more. But you can increase also the number of files. In Postgres, there is table space notion. If you put the table space not in 2 files, but in 40 files, and the probability of buffer latch on one page will decrease. No, this is not the way how Postgres works. Regardless of the number of files, the number of locks which service this will be the same, and the number of buffer partitions will be fixed. This is just a define. It can be changed and can be compiled in Postgres, but it doesn't depend on the number of files. Same with fast path. This define can be changed to increase the number of variables in the memory, and the situation will be better, but it's not related to the number of files. So this is not latch for the page, but let's say SQL servers, when such situation occurs, the latch is on the page, and if I increase the number of files, then probability will decrease. This is not a variable, it's more like a latch. It will hook to the page, and if I have one file and 100 processes, then the probability will be much less. In Postgres, this is not connected directly to files. We can discuss later with you separately, because I have other questions from the audience. Thank you for your presentation. Maybe I missed the beginning of the presentation. What's preventing configuration of the table, the level of config? Hypothetically, nothing prevents, because it can solve the problem or it can reduce it. In fact, the first problem, the answer is no. The problem is that if you're using too intensively one page, it will complete one of the locks. it will feel very intensively and it will use very intensively one of them. And insert will take the logs. It will go one by one until it reaches the log which is deadly blocked, and it will wait there. So the possible approach is to skip the bad buffer partition. This probably would have solved the problem, but this is not the way it's done so far. Maybe in the first case we can use read-only replica for Postgres. Yes, if we do read-only replica and put the load on it, then yes, it can. Maybe when we apply changes to replica, it can slow down. But if we distribute read-only load between several replicas to avoid too much load on one replica, then it would solve the problem. Okay, in this case, I see another problem in synchronization between the central node and the replicas. How fast it can happen, and the outdated data which is inserted in the master. Well, we have to monitor the delay of replica. We need to understand which LSA was applied to replica. There is a function to read it, and also the LSA at master. Usually they monitor, they build a graph to see the delay of replica. And even if you perform some transaction on master and then you look which LSN, you go to replica and you're waiting when this LSN will be applied. And we even created a separate patch with LSN team. It's not yet committed, but on the user level, it's possible to wait and then to do the selection again. Thank you for your presentation. My question is about if Maxwell process can solve this problem. The first two. Let's say I created a benchmark, and benchmark connects with 150 connections. If you reduce the number of connections, then there is no problem. But if you reduce... No, I mean the process. No, there is no conflict between the work processes. There is a conflict between backends of PG benches. I thought maybe they will queue, backends will queue. In order to avoid this contention, we need to reduce the number of backends. For example, connection pooler you can create, and in this way you will reduce the number of physical connections to Postgres. Another question? I would like to check. You started the PG bench on the same machine? Yes. I would like to add that I recreated maybe with exotic scripts with small latency because it's on the same machine, but this is why server is quite small and with not the worst num. So the latency of local connection and the latency of the node are very different. Let's say when we have several hundreds of cores and bad num, when latency to the neighboring node is too high, then with these machines it's much easier to recreate, but I didn't have it at the time, so I used a more typical one. I have time for one more question. No more questions? Well, in this case, thank you for your attention.